We have another example on the board. In order to find total impedance, I have to find first the capacitive reactance and inductive reactance, because capacitance is given and inductance is given. So I'm supposed to find first x of c is equal 1 over omega c, because omega is given, okay? And I have 1 divided by omega 1 times 10 to the 5th radians per second times capacitance 100 nanofarads. Close parenthesis. X of c is equal 100 ohms and angle of negative 90 degrees. So this is my x of c. Next, I'm supposed to find x of L. I'm going to write over here. X of L is equal omega L. Omega is equal 1 times 10 to the 5th, of course, radians per second, times L, which is equal 3 millihenries. This is equal 300 ohms and angle of 90 degrees. Okay, so I found x of c and x of L. Next I can find z total. Z total is equal R plus x of L plus x of c. I'm supposed to add all impedances together because I'm calculating the series circuit. So I have resistance equal 100 ohms plus x of L, which is equal 300 ohms, an angle of 90 degrees, don't forget about the angle, plus x of c, which is equal 100 ohms, an angle of negative 90 degrees. 223.6 ohms, an angle of 63.43 degrees. So this is the total impedance of my circuit. Next, I'm supposed to find voltage across the resistor. Right now, I don't have I total. I can find it, but let's say I want to practice the voltage division law. Okay, so we're going to right now write the formula for the voltage division law. So I have VR is equal voltage source times resistance over Z total. Again, someone can ask why you're using voltage division law if Ohm's law is easier. The thing is that I want you to simply practice the voltage division law. So if voltage source is equal 24 volts times the resistance, which is equal 100 ohms, over Z total, which is equal 223.6 ohms, and angle of 63.43 degrees. This is equal 10.73 volts, and angle of negative 63.43 degrees. So this is the voltage across the resistance. Next, I'm supposed to find voltage across the capacitor. So VC is equal voltage source times X of C over Z total. So I have 24 volts times X of C, which is equal 100 ohms, an angle of negative 90 degrees over 223.6 ohms and angle of 63.43 degrees, which is equal 10.73 volts and angle of negative 153.43 degrees. Okay, so this is the voltage across the capacitor. Next, we're supposed to find voltage across the inductor. VL is equal to voltage source times X of L over Z total, which is equal 24 volts times X of L, and we found X of L is equal 300 ohms and angle of 90 degrees over 223.6 ohms and angle of 63.43 degrees. This is equal 32.2 volts and angle of 26.57 degrees. Before we are going to go further, we're supposed to verify if our answers are correct. You're supposed to keep in mind that if you are going to add all voltage drops across each component in the series circuit, you are going to obtain the voltage source value. Okay, so let's check. We're supposed to use Kirchhoff voltage law. Voltage source is equal voltage across the resistor plus voltage across the capacitor plus voltage across the inductor. So we have 10.73 volts and angle of negative 63.43 degrees plus 10.73 volts and angle of negative 153.43 degrees plus 32.2 volts and angle of 26.57 degrees. Okay, supposed to add all these voltages together, and I got the value 24 volts and angle of 0.015 degrees. So now you're supposed to compare this value of voltage source obtained from the addition with the given voltage source. We got 24 volts and angle of 0 degrees, so we can say that our calculations up to this moment are okay. Now we are going to find the true power. So we have to start from writing the formula. P is equal 1/2, and because we found voltage across each component, I'm going to use the formula for power, which employs the voltages. Okay, so I have voltage across the resistor raised to the second power over resistance. Why I'm using 1/2? Because I'm talking about the peak voltage. So we have 1/2 times VR, which is equal 10.73 volts raised to the second power over resistance, which is equal 100 ohms. This is equal 575.66 milliwatts. Okay, so this is the true power in my series circuit. Next, I'm supposed to find the reactive power at the capacitor. QC is equal 1/2 times VC raised to the second power over X of C is equal 1/2, and I have 10.73 volts raised to the second power over 100 ohms, and this is equal 575.66 millivolt ampere reactive. Okay, so this is the reactive power at my capacitor. Next, we're supposed to find the reactive power at the inductor. So if QL is equal 1/2, and I have VL raised to the second power over X of L, which is equal 1/2, and voltage across the inductor was 32.2 volts raised to the second power over X of L. And X of L we found was equal 300 ohms. Everything is equal 1.72 volt ampere reactive. Okay, so this is the reactive power at the inductor. Next, we're supposed to find the total reactive power. So the formula says Q total is equal QL minus QC. Okay, so this is equal QL 1.72 volt ampere reactive minus QC, which is equal 575.66 millivolt ampere reactive is equal 1.14 volt ampere reactive. Someone is going to ask why we subtract these two powers in order to find Q total. To make long story short, we're supposed to realize that anytime we talk about the true power, we talk about the vector which has angle of 0 degrees, has certain magnitude and angle of 0 degrees. Anytime we talk about QL, we talk about the vector which has angle of 90 degrees. Okay, so I have QL. And QC is going to have always angle negative 90 degrees. Q total is the combination of these two vectors. Okay, so if you are going to add the QL to negative QC, you are going to simply subtract from QL QC. Okay, so this is just making the long story short. Okay, so that's why I subtract these two values, and I obtain the value of 1.14 volt ampere reactive. Next, we're supposed to find the apparent power. S is equal 1/2, and I have voltage source raised to the second power over Z total is equal 1/2, and I have voltage source equals 24 volts raised to the second power over Z total, which is equal 223.6 ohms. Everything is equal 1.28 volt ampere. Okay, so this is the apparent power in my circuit. Next, we're supposed to find the power factor. Power factor is equal cosine of angle theta. Theta is the angle which is next to Z total. So cosine of angle 63.43 degrees is equal 0.447, and because my angle is positive, or we can say that the inductive reactance is greater than capacitive reactance, okay? Or because we got positive value for Q total, okay? We're supposed to write word lag, right, next to the power factor. This is telling me that the current, the total current in the circuit is going to lag the voltage source, in this case by angle of 63.43 degrees. I'm supposed to use word lag. Now we're supposed to find the parallel equivalent circuit. In order to do so, we're supposed to find total admittance. So the formula says Y total is equal 1 over Z total. Now you're supposed to switch your calculators to the rectangular mode. Make sure that the answer which you are going to obtain is going to be in rectangular form. So simply write 1 over 223.6 ohms, an angle of 63.43 degrees. Okay, convert this to the rectangular form. You're supposed to obtain the value of 2 millisiemens minus J 4 millisiemens, where the real part is the conductance and the imaginary part is the inductive susceptance. Why? Because I have negative sign next to J. So what I'm supposed to do next? I'm supposed to find RP, resistance in my parallel equivalent circuit. This is equal 1 over G. 1 over 2 millisiemens is equal 500 ohms. Next, I can find XLP is equal 1 over BL, which is equal 1 divided by 4 millisiemens, an angle of negative 90 degrees, because negative J is equivalent to negative 90 degrees. This is equal 250 ohms, an angle of 90 degrees. Okay, so this is my inductive reactance in parallel equivalent circuit. Now we can draw the circuit, and we have so far RP, and we have inductor LP, and this is voltage source. We didn't find LP, so we can do this right now. In order to find LP, I'm supposed to use the formula for the inductive reactance. XLP is equal omega LP. So if you are going to solve this formula for LP, LP is equal XLP over omega. XLP we found is equal 250 ohms over omega 1 times 10 to the 5th radians per second. This is equal 2.5 millihenries. Okay, so this is my LP. Next, we're supposed to find the true power and reactive power in the parallel equivalent circuit. In order to do so, I'm going to write the formula true power in parallel circuit is equal 1/2, and I'm going to write voltage across resistor P raised to the second power over Rp. Please notice that the voltage source, right? Voltage source is going to occur across each component. So that's why I'm going to write that voltage source is equal to VRP, and this is also equal to VLP. So I have 1/2. I use half because we're still using peak values. So I have 24 volts raised to the second power over Rp, and we found that Rp is equal to 500 ohms. This is equal 576 milliwatts. Okay, so this is my true power in the parallel equivalent circuit. Let me remind you that we obtain the true power in the series circuit equal 575.66 milliwatts. Please notice that these two values are very close to each other, so it means that our calculations are okay. So let's check the reactive power. So I have QP, reactive power in the parallel circuit, so I can say that this is my QLP is equal 1/2, and I have VLP to the second power over X of LP equals 1/2, and I have 24 volts raised to the second power over XLP, and we found that this is equal to 250 ohms is equal 1.15 VAR. Okay, let me remind you that the total reactive power, Q total, in the series circuit was equal 1.14 volt ampere reactive. Okay, so please notice that these two values are very close to each other. So it means that we solved the problem correctly.